Hello, I welcome you all. The problem reads when crossing an intersection, a motorist encounters the slight bump or crown caused by the intersection road. If the crest of the bump has a radius of curvature rho equal to 50 feet, determine the maximum constant speed at which he can travel without leaving the surface of the road. Neglect the size of the motorcycle and the rider in the calculation. The rider and his motorcycle have a total weight of 450 pounds. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Hibbeler. Alright, so we have a motorcycle who is going over this hump and it has a radius of curvature 50 feet, and we've been asked to calculate the constant speed that he can travel over this hump without leaving in contact with the surface of this hump. Right, let's draw the free body diagram. I'll snipe this particular bike. You don't have to do this. This is just my preference. All right, so let's say there we go. The bike is somewhere there. So we are going to have, let's say the weight of the bike may be acting through the center of gravity, the bike and the person, like so. And let's say we do have the normal force also acting in that manner, like so. All right, and let's say we do have what else, our axis in this direction there. This is our axis, our n-axis. What else? Let's say we do have this one is our t-axis. Of course, along that direction we don't have any tangential acceleration. Tangential acceleration is equal to 0 because this speed that we are about to calculate is constant. So this is w, which is just equal to mg. This is n. This is n, and then this one is small n for the coordinate system, n for normal, and then this one t for tangential. All right, so we do have three conditions. We have the first condition where n is less than 0. This is where the bike is not in contact with the surface, and we have n equal to 0. This is where the bike is at the verge of losing contact with the surface. And then we do have n greater than 0. This is where the bike is in contact with the surface. So these three conditions, of course, for us we are using this condition at the verge. All right, so n equal to 0, so we're going to say summation of forces in the n direction. Let's show direction of the kinetic diagram. There we are, MAN, sorry, not this direction, this direction. Okay, this is our MAN. So of course, going down, being our reference positive, this is equal to MAN, where our AN is just equal to V squared, this centripetal acceleration, divided by rho, and we do have rho equal to 50 feet, and we want to calculate velocity. So what do we have? So we do have W minus N equal to mv squared divided by rho. but we are saying this is supposed to be 0. Therefore, we have mg equal to mv squared divided by rho. So this and this we can cancel out, and therefore our v squared will just be equal to rho g, squaring both sides, and we calculate. Then we'll calculate to say our v therefore will just be equal to our rho is 50, our g is 32.2. Okay, and therefore our v, this is the maximum, our v will just be equal to, that's 50 by 32.2, square root of this just gives us a 40.12. This is feet per second. Alright, so again 50 by 32.2, square root of that, that's 40.12. Okay, so there we go. We've calculated our velocity, which is a 40.12. This is the maximum that the bike can go so that it still remains in contact with the surface at that particular hump. So I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye. See you in my next screencast.